right, everyone. I am here with Gustavo Malkomes. Gustavo is a research engineer at Intel by way of their recent acquisition of SigOpt. Gustavo, welcome to the TWiML AI podcast.
Thank you very much for having me in the show.
Hey, I'm really looking forward to digging into our interview, but of course, I'd like to have you share a little bit about your background and give our audience an opportunity to get to know you better. Tell us a little bit about your journey to machine learning and AI.
Awesome, absolutely. Well, first, I'm originally from Brazil. I'm a computer science by training. And when I did my undergrad, I went to a very good school in my region, but machine learning wasn't a strong topic. But fortunately, the internet was very generous with machine learning. We had the opportunity to basically watch Professor Angel NG to talk about machine learning on YouTube 12 years ago, I think. So my friends and I created a study group to study machine learning. And maybe I can say that he was my first instructor to the topic. After that, I worked in many machine learning projects. I decided to do my PhD in the US. I remember checking all the faculties that I could work with that worked with machine learning and counting how many publications they had on ICML and NeurIPS. I don't recommend this to be a metric to consider when you're choosing between grad schools. But 7 years ago or something, I was super excited about working with people who actually did machine learning. And that's one of the things that I actually evaluate. Seems silly to say now. And then that's how I began my journey into the field.
And you ended up for grad school here in St. Louis at WashU, is that right?
Yeah, exactly. I went to WashU under the supervision of Professor Roman Garnett. I was actually very fortunate to work with many intelligent researchers throughout my career, of course, my advisor being one of them, but also Professor Ben Mosley, which is now at CMU, Professor Killian Weinenberg, who is now at Cornell. So I was very happy with all the collaborations that I did throughout my career, and I continue to do so.
And you mentioned your school in Brazil. Where was that?
It was the Federal University of Ceará. In Brazil, the federal universities are typically very good, and that's basically it.
And that's northeast, like Fortaleza.
Exactly. Good that you know that. We had like the World Cup in my city too. One of the big games was there. Of course, as a Brazilian, I don't want to remember the World Cup in Brazil because we lost 7-1 to Germany. But yeah.
Nice. And for your graduate work, what did you study? What was your dissertation on?
Of course, yeah. So as I said, like I worked with different topics in machine learning. Mass scale clustering was one of them, multi-agents. But I fell in love with this topic that I like to call active learning. So my dissertation was about how we can use active machine learning to create better tools for machine learning itself. It's kind of like an automated machine learning scenario. And specifically, I think that my main area of expertise is how we can actually make decisions under the face of uncertainty. That's what I typically call active learning. Any kind of decision tool, any kind of decision problem that we have to solve, where we want to gather new data to accomplish a specific task. And I've done this for a hearing project where we improve the performance of a screening test for audiometry. That was very, very cool. It's under the same setting. To do model selection with the same pipeline where you actively select models to train. And of course, with Bayesian optimization, which is what I've been doing since grad school, but also in my work at SigOpt, how we can make effective decisions to optimize functions very, very fast, specifically black box functions.
And we'll be digging into that topic in quite a bit of detail as we talk through your spotlight paper at ICML, which is Beyond the Pareto Efficient Frontier, Constraint Active Search for Multi-Objective Experimental Design.
It's a long
But
name.
it is a long name, and we'll unpack that name. But before we do, you referenced active learning. You also referenced it in the paper. But my sense is that you think of it in a slightly different way than is commonly construed. So when I think of active learning, I think of machine learning approach or algorithm that um, takes an active approach to data selection so that the model can be trained in a more sample efficient way, to put it simply. But you think of active learning in a much more broad way, I think. Can you kind of connect the two?
Yeah, of course, absolutely. You're perfectly right. The most famous examples of active learning are when you have a model and you want to select training data to create this model faster. What I
Hmm.
mean by create, I mean achieve some accuracy faster than if I use the whole data set.
Right.
I basically want to make smart decisions about my training samples to avoid waste of resources.
Right.
I think in real life, there are like many opportunities where we can use the same setting, the same tools, and the same mechanism to solve more broad problems. So, in the case of optimization, the data that we're going to collect are is basically parameter configurations that we can test and evaluate if they are helpful for our application, which the goal is not to improve accuracy, but it will be to, well, it could ultimately be, but typically it will be to maximize the function.
Hmm.
So any kind of sequential decision making tool, we can also call sequential decision making, but trained on machine learning, I like to think that active learning is as broad as supervised learning, reinforcement learning. We can think about this very general framework that anytime that we are collecting data, we can do so in an efficient way to achieve a specific goal. So three examples are, well, one, typical active learning where your goal is to give information about your model faster. That ultimately would be the case if I'm trying to learn this decision boundary very, very fast, typical case.
Yep.
Bayesian optimization, where we want to optimize functions. So the data is the parameter configurations, and the goal is to find the highest values. And another example is drug discovery, where you want to find new components or biology. You want to find new chemicals to achieve some properties, and or perhaps even more broadly, experimental design, where you want to understand the whole physical phenomena very, very fast. You could say that active learning is kind of science more generally. We are all every time building models and collecting new data to validate those models. So that's kind of my general idea for that. I know that I talk about different subjects, but I'm happy to clarify any of them.
Hmm. Hmm. You mentioned the you mentioned this chemical engineering scenario example, and that was one of the background problems or motivations for this paper. Can you tell us a little bit about the problem that you were trying to solve that led to the work discussed in the paper?
Yeah, of course. So first, this is a joint work with my colleagues at SigOpt, Harvey Chen, Eric Lee, and Michael McCord. And Harvey and Mike, they had this collaboration with members of the University of Pittsburgh, the Laboratory of Advanced Materials at Pittsburgh, directed by Professor Paul Liu at the University of Pittsburgh. And they have been collaborating with this idea of creating new materials using machine learning. Specifically, they're interested on creating new types of glasses that can improve the performance of, for example, solar panels. The idea is to have durable, anti-reflective, anti-soiling, self-cleaning glasses for solar modules. Basically, the problem is you want to improve the efficiency of solar panels by changing the properties of the glass. You don't want, for example, glass or reflection in the glass, because the light will basically bounce off of the glass, and you basically will be losing energy. Also, if the glass is dirt, that's a problem too, because it blocks the light to come into the solar panel, and you also lose efficiency. What what the researchers from the University of Pittsburgh they work with is creating like small structures, nanostructures on the top of this glass to change the properties of light and therefore improve the performance of the solar panel. So the idea is, and this is very common in many different material sciences and other types of science work, is they have numerical simulations, they construct designs, they can fabricate designs using computer simulation,
Mm-hmm.
and using the software they can understand trade-offs for ultimately creating a structure in real life. What we have observed is that this is very different. It's very different to create a new material in the computer versus creating a new material in the real life. And the reason for that is in the numerical simulation, we don't have all the properties. We cannot perfectly simulate everything. There is a
Right.
correlation. We can get a lot of this. But ultimately, the equipment that we're going to use to produce the materials will be slightly different. We don't have like infinite precision, or something different happens in real life, because that's how
Mhm.
real life is.
So it ends
Um,
up being that the simulation is producing a set of candidates, but you ultimately have to fabricate some small number of those candidates and see how they perform in the real world.
Perfectly. That's exactly it. We have this human in the loop. That's a very common term right now.
Hmm.
That basically requires the machine learning tool to assist the decisions that the human expert that knows everything about the problem, knows everything about the domain, can ultimately do and select. I
Hmm.
think that's the main insight that we want to bring to this paper, talking in a real life, in a real high level. There is a development scenario, there is a production scenario, and there's probably a discrepancy. And ultimately, there is a human in the process doing supervision of the whole decision making and being powered by the experimentation process that we do offline, but which eventually will be very costly to do in real life.
Hmm. Hmm. So let's maybe return to the title of the paper and start to kind of unpack some of that, so we can dig deeper into what you've actually done. So again, the paper is Beyond the Pareto Efficient Frontier: Constraint Active Search for Multi-Objective Experimental Design. It sounds like the problem that you're seeking to tackle is multi-objective experimental design. How does that relate to the scenario that you just outlined in for the materials?
Yeah. So material experimental design is basically this field that do smart decisions about designs. And the designs could be like many different things. It could be actually a whole experimentation pipeline in a lab. In
Hmm.
our case, just to keep with a real example, it's going to be the structure that we want to really create on top of the glass. The
Yeah.
cone, the box size, all the properties that we can actually use to create those structures.
Okay.
Okay, that's the experimental design part. Um, Multimetric, it's because in many problems in real life, um, it's very, very hard to find one thing that we care about. So there are competitive objectives. If we change how the light reflects on this glass, another property will be different.
Hmm.
Transparency, oil contact, cleanness, all those things really related to the subject will change. And ultimately, they will be competitive. That what typically makes the optimization problem a little bit harder. And one thing to highlight here, which is very general, um, is the way that we are doing experimentation is really through smart decisions. We don't have access. We are solving an optimization problem, which is black box. We will really run the simulation to get an output, but we don't have access to gradients, for example. So it's really like a black box that we put inputs and we receive outputs back. We want to design experiments, basically design input configurations that will give good results on the outside here, on the Y values. If we're talking about optimization, we're trying to optimize, minimize, or optimize one of those goals.
Mm-hmm.
Now, the Pareto efficient frontier, it's basically how we try to solve multi-optimization problems, multimetric optimization problems. We traditionally want to find output values that can dominate the other ones. The hypothesis here is that we cannot compare the two metrics. For example, risk and return, if we're talking about finance.
Mm-hmm.
And there's no really like solution for this. It's really dependent on the user to decide the level of risk and the level of return it's willing to take.
Mm-hmm.
So in that sense, all the configurations that we can return to the customers that dominate the other ones. So if I can improve my return without reducing the risk, that's better than a suboptimal configuration that has the same risk level but a lower return.
Right.
Why I would want this, it doesn't make sense. So I would actually have the dominate solution, which has a higher return, but the same level of risk. That's how we construct the Pareto efficient frontier. And this makes a lot of sense if you're probably choosing maybe stocks. But in problems that we're trying to understand the metric values and the parameters, we really want to focus on the search aspect. What I mean by this, for a scientist, for example, they will be very happy if we give them a material that has very nice properties, but they will be very confused if we change the parameters that create this design slightly, and the result is really bad. So
Mm-hmm.
they're looking for really a broader sense of what's happening here, not only with the metric values, but also with the parameters. Ultimately, they want these stable parameters that can lead to consistent results. Why? Because as I said, the production and the development and the production settings won't be a perfect match. They really want consistent results. That's the motivation for why we're talking about an alternative to this multi-objective solution for experimental design. It's because people care about both the metric values, but the parameter values. They want the stability. They want to understand the problem they're trying to solve.
Mm-hmm. So just let me try to replay that so that I make sure I'm understanding it and we're all on the same page. You've got this notion of the Pareto efficient frontier. We know it from finance and economics and problems like that. And that says that in the case of a two-dimensional relationship, there's a line that is your optimal trade-off among these values. Um, and what you're suggesting is that in the real world, for example, when you're designing a material, uh, a value on this Pareto efficient frontier might be optimal from the perspective of the metric, but it might be unstable. If we think about kind of the optima the chart of the optima like a curve, it might be sitting on a spike, and so if you shift one of your parameters, it might your metric might drop off precipitously, whereas something that is theoretically less optimal might be sitting on a broader base. And uh, I think ultimately the result is it would be easier to produce in the real world because it's not quite as unstable. Is that the idea?
That's the idea. If you think about I think when you're talking about optimization, it's very common to think about climbing a mountain, right?
Hmm.
Of course, in our scenario here, we don't have derivatives, but we can
Because it's
theoretically
black
think,
box.
yeah, because it's black box, but you
Hmm.
can theoretically think about a surface of function values that exist. And we
Yep.
can pretend that this is like a mountain.
Hmm.
And the metric values will be basically the height of this mountain.
Right.
So in a multimetric problem, it's kind of like we are trying to find the optimal of the function values between two mountains. Let's say there's a mountain number 1, which is one metric. There's a mountain number 2, which is the second metric.
Hmm.
In a multi-metric optimization problem, we want to find really the peak of the mountain, the highest value possible. And the Pareto efficient frontier will be basically a line between those two mountains on parameter space. That's exactly the Pareto efficient frontier on metric values, how they will be translated to the parameter space. It's going to be a line. If I navigate towards the other mountain, I'm going to reduce the metric values here, but I'm going to improve the metric values here.
Okay.
So
And
what
just
we are trying to,
to jump in there, the dimensionality of the parameter space is like the number of dimensions of your mountain essentially, and then the number of metrics is the number of mountains.
in some sense, yes.
Okay.
That's a very good analogy. Yeah. So in this case here, we're talking about 2 and 2,
Okay.
but it could be, in a more like in a more complicated surface in the world, will be like a 3-dimensional shape. But anyway, the point
Yeah.
is, if we have two metrics, there is one optimal value here, another optimal value here. The Pareto frontier is going to be a line that trades those two off.
Hmm.
Now, what we are saying is, okay, this is only true during your development setting. You find the optimal values here during your numerical simulation. But what if the mountain shifts a little bit? The line was going to be completely different. So do I really want to return to the expert, to the human, only the points that could be, suboptimal in the real life because the mountains can shift slightly? The
Hmm.
answer is no. We probably want to give them like more information. We want to give them enough information so that even if the mountains change a little bit, you will still be comfortable with the results that you get. Does that make sense?
Yeah, I guess it raises a question for me. Are we trying to is the idea fundamentally that we're going to be less restrictive in the values that we return? We're going to be looser and allow the human in the loop to, because we know there's a human in the loop, they can determine ultimately what's the best point for them? Or is it that somehow the algorithm that you've created also incorporates stability and returns better points that aren't on the Pareto efficient frontier? Do you
That's a
understand the distinction I'm getting at?
Yeah, it's definitely different. I totally agree with that. And I would say it's the former.
Okay.
And the second option, the latter, could be
Mhm.
our next paper.
Got
but
got it.
it's more on the former, in the sense that we will do exactly what you described. We're gonna lose the definition of best to not really the peak and top of the mountain, but to an altitude that is good enough.
Mhm.
So we're gonna have like the whole shape of the top of the mountain, and we're gonna offer this to the user somehow. That's the part that it's the problem formulation aspect of this. We are generalizing something called Bayesian optimization, which really cares about the highest values, and experimental design, which wants to understand the whole mountain, all the shapes and configurations of the mountain. Sorry. Um, Constraint Active Search, which is exactly the problem that we are proposing to solve, is really a
Mhm.
search problem in the sense that we want to find structures in the parameter space in this active learning pipeline, which are constrained by metric values. Specifically in the paper, we say that there is a region of satisfaction, or a satisfactory region, where it's the parameter configurations that lie above the metric values. You can also think about this feasible region, but typically feasibility means that we have constraints on the parameters. And for some reason, we don't want the parameters that are not feasible, right?
Right.
Here, we are really losing the problem from the optimization to something that is not the best, but it's satisfy the constraints.
So feasibility typically speaks to the parameters. Satisfaction in this case, you're more speaking to the metric or the objective.
Exactly. We want to loosen up the definition of what is best on the metrics. And again, this is black box. We don't have this beforehand.
Hmm.
So
Right.
again, with the example of the mountain, we want the whole shape of the top of the mountain, not necessarily the peak best value.
Hmm. And thinking about it in the context of the mountain, what's the relationship between the satisfying construct that you're creating and the idea of like global optima versus local optima, that kind of thing? Is the thing that connects those the idea of stability that we talked about earlier?
In some sense, yes, um, because the optimal values will be within the satisfactory region. So we are just expanding the notion of what is good to more values based on the constraints that the user gave us on the metric values. So,
Mm-hmm.
for example, suppose that we want to find high performing machine learning models, and we care about accuracy, but also inference time. I want to give you a list of different models, and diversity here is the key for constraint active search that satisfy your constraint on accuracy above 80% and inference time, less than a minute, let's say. Hopefully, way less than that. But I'm going to give you an option. The solution for this problem is going to be a list of options that you can trade them off,
Hmm.
both in terms of the metric values, but also on the choices of hyperparameters that you have. For example, number of trees, if you're talking about XGBoost, and all kind of like any kind of parameter that you think is important for creating your machine learning model, which are the hyperparameters.
Hmm. Okay. Okay. And so you've created this, you've kind of redefined or defined a new problem, constrained active search. Do you also share any insights into how to solve the problem?
Yeah, absolutely. That's the main difference between the workshop paper that we have published like a couple of months ago last year
Okay.
and the and a full publication in the ICML is the fact that we have a solution for this
Okay.
problem. um, so I hope it's very clear that like why I'm stressing the problem is because it's a different mentality. We're changing the focus from getting the best possible values to getting high performing values, high performing models, high performing designs, which means that I can accept in a continuous space a bunch of new points. And if I can change slightly the same configuration and or parameter and get the same results. So that's
Mhm.
something that it doesn't make sense mathematically. So you want to incorporate something which is diversity. And I think this is really, really important for many real life applications, especially and I can talk more about this next, in the context of developing machine learning models, developing real materials in real life. But to the technical aspect of the work, we use something called Bayesian decision theory to derive an algorithm for solving this problem. And as I said, the main property of this problem is we want to find a set of solutions in continuous space. So we want those solutions to be different in parameter space. We don't want to lead to the same design. If I show this to a scientist, a box, this nano structure that I've changed like 1 nanometer up or left, or the cone in the height of the cone or
Mhm.
the shape slightly, they would say like, yeah, this is the same thing. I don't care about that. I can't even produce this difference. That's also important. But anyway, the way that we focus on tackling this problem is defining something called the, the utility function, which defines how our active learning, active search algorithm will um, select the next configuration. So to give you an example, in optimization, what we typically care is if I have a configuration that has this value here, I care about new configurations that can improve the value that I've observed. So this leads to a policy that is expected improvement, how much I can improve over the last observed function value. We don't care about the best values per se. We care about two things in this problem. We want to satisfy the constraints. That's the very first important thing. And two, we want the solutions, the parameters that we select, the designs that we select, to be different. So if I choose two new configurations that satisfy the constraints, but they're very close to each other, I don't want this. So we define something called the neighborhood of a point. So any configuration that we choose in parameter space will basically induce a volume on parameter space. And this volume is exactly what I want to increase. I want to increase the coverage of my configurations. Where coverage I'm defining as the volume on parameter space that is potentially above the threshold. That's something complicated. I definitely recommend you to see the detail, or your audience to see the details on the paper. But that's the intuition. We want points above the constraints that satisfy all the constraints. And we want points that are not too close to each other so that they can lead to diversity.
And you said that this is a complicated part, but when you talk about the threshold, is that a a coverage threshold, meaning the kind of the union of the volumes around the individual points and the degree to which that covers your entire space, or is the threshold specific to each point in the parameter space?
The threshold that I mentioned was specifically to the metric values.
Okay.
So basically is the level, if you go back to the mountain again,
Right.
and I'm going to use my fingers here to point out, and I definitely recommend you to check out the paper, which we have better visualizations for that. But if we talk about the top of the mountain, we are chopping off the top of this mountain in some region.
Yeah.
So the shape could be really pointy, or the shape could be like really wide. So the threshold really defines the shape here, the level that we want to cut off the mountain. Now, the coverage that I was talking about is really like, if I want to place a point here in this side of the, this is funny. If I want to place a point on the top of this mountain, I basically want to solve a packing problem. I want to know how many configurations I can place on the top of this mountain.
Got it.
In a way that it covers the whole parameter space.
Got it. Got it.
Does that make sense? I think the packing
So
problem is
packing or tessellation, you want to pick your points to maximize the coverage of I guess, this part of the mountain that you've cut off.
exactly.
And
Because
you define the points by some kind of radius around the points.
right. In our algorithm specifically, we have a parameter that we call radius R, which defines in your application how much you care about distance. So basically, this parameter is telling me that if you find two configurations that are too close, according to this distance, that's exactly what this parameter is measuring. I don't care about this. It doesn't increase my knowledge about the problem.
Yeah.
So this radius defines the minimum level of proximity that you can have between 2 points. And again, the top of this mountain, this region that we want to cover, is really the region of parameter configurations that yields high performing values.
Right. And is there, just out of curiosity, I'm wondering to what degree you could characterize the total volume of the top of the mountain, and could you like back your way into R by saying you want 20 points, and the volume at the top of the mountain, and so like divide the volume of the mountain by R. I'm sorry, divide the volume of the mountain by the number of points and kind of back into your R value, or are there things there that we don't know or can't figure out or are really difficult?
Right, that is an excellent question. But the setting is we don't know. Basically, we construct probabilistic models that talks about the surfaces of the objective functions that we want, basically. And the surrogate model, the probabilistic model that we have, is going to give us a notion of uncertainty of the shape of that we are trying to solve for. So nothing we know for sure. We are actually discovering this through experimentation. We are increasing our knowledge or our ability to model the surface of the metric values, and also really the region of satisfaction. So in reality, the utility that I just described is true, fixed the mountain shape, if you will. But what we really implement is the expected gain in utility, which takes in consideration our uncertainty around the surface.
Okay.
So if you're asking about how many points I can place, it's really through experimentation. The more points you give us, the better to solve the problem. There is a rule of thumb of 20 to 30 times the dimension of the input. It's a good number if we really have good priors to match your problem. But theoretically, this could be you might need way more points.
And you've mentioned Bayesian optimization previously, and now we're talking about surrogate models and priors. Can you talk about where Bayesian optimization fits into this and how, and where the surrogate models come from?
Exactly. Yeah, absolutely. So I think it's let's think about like the complexity of those problems. If I want to solve a single problem, just one metric, I'm going to do Bayesian optimization to find the best values. What I'm going to do, I'm going to create a surrogate model that does this inference over the function values that I haven't observed yet. And I'm going to create an acquisition function, which, as I said, it's basically a policy that tell us which point I'm going to choose next. When I'm talking about multimetric problems, I can also use Bayesian optimization. I can also use Bayesian optimization with constraints. But again, everything that I'm focused here is to construct surrogate models, one for each metric, and trying to find the hypervolume of the Pareto frontier. Again, the Pareto frontier is this region of dominant points. The hypervolume is a metric that tells me if I increase those values, I will be doing a better job at finding the Pareto frontier. The next step for this is, at least in my mind, there's a different problem that is important to highlight, which is called level set estimation. It's when I'm not interested on the best values per se, but I'm interested on finding the threshold, really where the function values will change from the level that I stipulate, basically the constraints in this case. What we argue is constraint active search, it's a generalization of this. In hindsight, if you knew the best value, something that we don't know, but if you place the highest function value on the constraint active search formulation, we would recover Bayesian optimization, because again, the definition will be just the peak of the mountain. I just want to return the best values. So I recover Bayesian optimization with this constraint active search formulation. The opposite of this is if I knew the minimum value of all the metrics, I could plug this in my constraints in constraint active search, and I will recover a problem that is experimental design. Is really, I want to know the function values everywhere. Constraint active search is something in the middle. You choose the thresholds the way that you wish. And of course, we recommend you to do so in a conservative way, because everything about the function we are learning on the fly.
Okay.
So if
I'm
you
not
start,
sure
yeah.
I was just going to say, I'm not sure I fully follow that, but I think in essence, what you're saying is that there's a relationship between this problem that you've articulated here, constraint active search, and other things that we've studied for a long time, Bayesian optimization, level set estimation, and experimental design.
That's the gist. Yes.
Got it. Okay. Okay. And I'm first, did we get through the kind of the explanation of the mechanism? I think we did get through it, at least conceptually, in talking about the volumes. If there's any pieces that we have not covered. Jump in with those, but I'm starting to think about, okay, how do you assess performance here, and measure the effectiveness of the method and what that even means in this context.
Precisely. So for the algorithm, really, it's hard to talk more in detail, like in more details about it, because you have to know some mathematical definitions of neighborhood. I think we covered the high-level idea
Okay,
in a good sense, which is really trying to solve the stacking problem in the high-performing region of the primary space.
got it.
But ultimately, we define a utility function, and we do something that we do in Bayesian decision theory. We select the action that maximizes my expected utility. And the utility is this volume that we define. The uncertainty on this utility is on the real region of satisfaction, which is, the thresholds. Because we're using probabilistic models, we can compute what is the probability of any configuration to lie above the thresholds.
Mhm.
And that's defined basically as a whole set of points in expectation that will be within the region of satisfaction.
Okay.
What was your next question? Sorry.
So then what does evaluation look like?
Exactly. So in our experiments, we tried to be very we were very honest. We didn't try to, but basically we had multiple ways of looking about the quality of those results.
Mm-hmm.
So we consider like 4 metrics. One of them is just the number of positive points that you get, the number of points above the threshold. If your problem is really, really difficult, that's something that you might care. But if you just optimize this metric, you might not get diversity,
Mm-hmm.
which I think it's a very important thing in our problem. The second angle that we can look at this is really, what about the hypervolume? What about the quality of the points that we get above the threshold? Are they dominant points or not? This is what the hypervolume is measuring. It's a standard metric for optimization problems. But for our problem, what we really care is diversity of the points that lie above the threshold, that satisfy the constraints. So we measure this in 2 ways. The very first one is using the field distance, which is a typical measure of diversity in many areas. It basically the radius of the the largest ball you can place on the points that cover them. It's the largest radius that you can use to cover all the points.
Mm-hmm.
That's kind of the definition of full field distance. And a new criteria that we use to tackle this problem, which is coverage recall, which is really how much volume I was able to recover from this satisfactory region. This is only possible to compute if we know the ground truth, of course, but it's definitely something that measures the success of constraint active search.
Yeah. And what kind of results did you see?
Oh yeah, we basically do pretty
And
well.
to jump in, are there is the problem that you've defined close enough to existing problems that there are benchmarks that are relevant, or is evaluation mostly self-referential? And so,
Well, our goal with this experimentation setup was to show like those 4 metrics and really highlight that different problems, different strategies are solving different things.
mhm,
So the algorithms that we propose to solve constraint active search, we actually propose 2 or 3 alternatives, and they all do very, very well on coverage recall and field distance.
mhm,
Specifically, the main algorithm that we propose, expected coverage improvement, is doing really well in minimizing the field distance and maximizing the coverage recall, which is exactly what we want.
got it.
If we look at the angle of optimization, you will see that Bayesian optimization with multiple metrics will actually be the best because it's the only algorithm that is really trying to do that. And if we look at the sheer number of positive points, there's another line of research called active search, which optimizes the number of positive points. The downside of that approach is diversity is compromised. And this is true for both problems. Bayesian optimization doesn't have as much diversity as constraint active search. Active search doesn't have the same ability to optimize hypervolume nor increase diversity as active search. It just finds a bunch of positive points and
So,
they're close together.
right, restating, Bayesian optimization will give you the points that are optimal we talked about, but not necessarily
Di-
stable or diverse. Active search just gives you back a bunch of positive points, and so creates a lot of noise for the human in the loop to go through. And because the points are clustered together, it's not particularly meaningful distinctions. And so the diversity formulation and constraint active search produces something that is much more useful in a real world human in the loop scenario.
Exactly. And I would like to dive deeper on that, why we think this is very useful.
Hmm.
Um, just in benefit of active search, this is typically a solution that is offered for discrete points. So if you have discrete points, maybe you should do active search, and you care about, and like they're very rare to find. In this scenario where we have parameters that are continuous, then constraint active search will be the best trade-off between finding good values, kind of the hypervolume, and diversity.
Got it.
Now, if we go back to how this is really useful in practice when we have a human in the loop, the reason for that is if we actually solve optimization problems and we offer experts the decision on the Pareto efficient frontier, they will typically will think that they can choose metric values, and specifically in this case of design, they would try to see metric values that satisfy their preferences in some way. They will look at the function values here. Oh yeah, this configuration is really good, and I see a couple of points nearby. They have the same performance of this one. But the problem that they could face is when they map back to find how I'm going to produce this design. Maybe those metric values that were close here in the metric space could be really all over the place on the parameter space. And
Hmm.
this doesn't increase their confidence about the ability to produce a specific design with this height or this width. On the opposite, constraint active search will provide not only points on the Pareto frontier, but also a bunch of points they're not, uh, uh, they're like dominated by the points in the Pareto frontier, but they are a bunch of points that in the parameter space, they will offer you insights on how I can actually produce and create this design.
Hmm.
That's one of the things we think this is important. The other one, it's really respect to the application. For example, some of those metrics that they care to, so basically we have this human in the loop. We want to use this experimentation to guide them their choices. Eventually, they will choose 5 or 10 designs to produce in real life. They will fabricate the designs. Diversity plays a really important role here because when we actually compute the designs, you can further measure properties of those designs. And if they are all very different, then you can further do like a more expensive test to really find your best solution.
Yeah.
Now, we can also translate this to machine learning in real life. Ultimately, we have business metrics that we care about, and the validation metrics that we use are a good proxy of what we can do during production, but maybe are not perfect.
Hmm.
So what we want is offer users the possibility of having very different models so that they can use those models in a more complicated testing setting. For example, as a shadow of a current system, or in an A/B scenario where they want to evaluate things that they couldn't in during development because the data is different, and having the ability to test more different models in the semi-production system is really, really helpful for them to make sure that the models that they created using all the metrics developed previously are actually helping them to achieve the business goals.
Hmm. Hmm. So, returning to this theme of performance in development versus performance in the real world, but here in the broader machine learning application as opposed to the engineering application.
Yes, exactly.
Awesome. Awesome. Um, my kind of next question would be to ask about, where you go from here and future directions, but you already said that it's, returning back to the objective and trying to understand uh stability for some of these points as one potential direction. Any other thoughts there?
Well, this is a new formulation, so we are excited to invite researchers from the community to think about different properties, different algorithm, different ideas. We in this current formulation we have this parameter R, which it's something that is a function of your application. In real life, we can probably design a schedule for this parameter. We start with very large R values that will do a lot of exploration, and then we reduce the R values so we can actually find a bunch of models more similar in some sense. We have some also theoretical understanding of the problem. We prove that this algorithm has a bound on the field distance, which means that it's able to converge in the sense of covering the satisfactory region. But you can also think about developing other results, but which we haven't done in this paper,
Other
about how many
theoretical results?
other theoretical results
Mhm.
about the number of points that I need to at least get a notion of convergence closer to the results that we get on Bayesian optimization,
Mhm.
for example.
Yeah. Awesome. Awesome. Well, Gustavo, thanks so much for taking the time to share a bit about your paper. Very interesting stuff.
Thank you very much. I really appreciate it. It was a great conversation.